What would happen if a watermelon hits the Earth at the speed of light? Okay, let's imagine a 10-kilogram watermelon crashing into the Earth at 1x the speed of light. Whoa, the moment of impact would release energy equivalent to the explosion of 2 million tsar bombs. First, the watermelon would interact violently with the atmosphere. Air molecules can't get out of the way in time and are smashed apart, triggering nuclear fusion. This fusion would emit gamma rays and X-rays, which would instantly ionize the atmosphere into plasma. Creatures on the ground would first be killed by this radiation. At the same time, the supersonic shockwaves generated by compressed air would destroy everything in their path. They might even blow part of the atmosphere into space. Well, upon impact, the remaining energy would pierce the Earth's crust, creating a crater several kilometers in diameter. It would also trigger super earthquakes of magnitude 15 or higher worldwide, along with large-scale volcanic eruptions. The shockwaves would travel around the Earth multiple times. After this collision, dust and volcanic ash would cover the Earth's stratosphere, creating a nuclear winter. Sunlight couldn't penetrate through, causing the ground temperature to drop by dozens of degrees in an instant. Plants would die from lack of photosynthesis, the food chain would collapse, and animals would go extinct due to hunger and cold. The dust cloud could last for decades, and it might take millions of years for Earth's ecosystem to potentially recover. Let the Earth's mass increase, and then make Jupiter a satellite of the Earth. Alright, for Jupiter to orbit the Earth stably, the Earth's mass must be far greater than Jupiter's. Generally speaking, the mass of the central celestial body needs to be at least 10 to 20 times that of its satellite to form a relatively stable system. Okay, so we'll increase the Earth's mass to 20 times that of Jupiter. Wow, the Earth's appearance changes in an instant. Oceans, mountains, and continents we're familiar with vanish in the blink of an eye, crushed into its scorching, high-pressure core. At this point, the Earth looks like a brown dwarf. Its interior may undergo mild deuterium fusion due to extreme pressure, but not enough to become a true star. Next, we'll replace the Moon with Jupiter. Despite its enormous size, Jupiter is now just a satellite. It will orbit the super-Earth along the Moon's original orbit. Orbiting each other at such a close distance, the surface temperature of both planets reaches as high as 500 degrees Celsius. Well, the super-Earth's massive gravity will exert a noticeable gravitational tug on the Sun, causing the Sun to also move slightly around the barycenter of this new Earth-Jupiter system. The orbits of the solar system begin to destabilize, and the total mass distribution of the solar system undergoes a drastic change. The sudden appearance of a celestial body with a mass close to that of a brown dwarf in the inner solar system will severely disrupt the orbits of all planets. Mercury, Venus, and Mars in the inner solar system could be flung out of the solar system by the super-Earth's gravity, crash into the Sun, or be captured and swallowed by the super-Earth. For Saturn, Uranus, and Neptune in the outer solar system, their orbits will become extremely unstable. They might be ejected into deeper interstellar space, or enter highly eccentric elliptical orbits and collide with other celestial bodies. What would happen if we turn the Moon into a planet of pure water with the same mass? Alright, let's transform the Moon, all 73 quadrillion metric tons of rock, into pure water of equal mass. Whoa, its appearance would change right away. Its radius would expand from 737 kilometers to nearly 500 kilometers. Its apparent diameter would increase by nearly 50%, turning from a small silver plate into a translucent jade disc. At night, it would light up the roads so much you wouldn't need streetlights. It would even look like it's breathing. During the day, the lunar surface temperature would soar to 127 degrees Celsius. In a vacuum, ice would boil instantly, releasing a thin layer of water vapor, like wrapping it in a white veil, and its brightness would soften. At night, the temperature would plummet to minus 173 degrees Celsius. The water vapor would then condense into ice crystals and fall back to the surface, making the ice shell shiny again, like a glowing snowball. This breathing layer would form a thin atmosphere. Because the speed of water molecules is far lower than the escape velocity of 2.4 kilometers per second, they won't escape all at once. What's more, the water on this water planet would exist in three forms. At its core, 500 kilometers deep, the pressure, 400 atmospheres, would squeeze water into ice 7, which is harder than steel, like a water diamond hidden at the center. The middle layer, 500 to 500 kilometers deep, would be regular ice, as brittle as fully frozen ice cubes in a fridge. The outermost layer, 100 kilometers deep, would be the active zone, boiling during the day and freezing at night. But don't worry, the tidal force wouldn't change. Since the Moon's mass wouldn't change, its gravitational gradient on Earth would stay the same. People who go tide pooling could still wait for low tide on time, and the Qiantang River tidal bore would still arrive as scheduled. The only downside? It would slowly lose weight. Without a magnetic field to block the solar wind, a small amount of water molecules would be blown away. But the mass lost each year would be less than 1/quadrillionth of its total mass, so it would remain Earth's bright neighbor for 10 billion years. What happens if Earth's density is multiplied by 6? Okay, let's instantly increase Earth's density to 6 times its original value. Whoa, Earth's volume shrinks instantly to roughly a sixth of its original size. Its radius is cut in half, from over 6,000 kilometers down to 3,500 kilometers. Right now, Earth is even smaller than Mars. Its mass stays the same, but with a smaller radius, gravity is totally different. Surface gravity would become 3.3 times stronger than it is now. If you weigh 60 kilograms today, you'd weigh 200 kilograms then. Gravity would make your spine creak. Olympic high jumpers could only leap 30 centimeters, and even sparrows wouldn't be able to fly. Because of the sudden density spike, Earth's crust would go from 2.7 grams per cubic centimeter to 16.2 grams per cubic centimeter. Tectonic plates would break apart and rejoin under their own weight. This would trigger global super-earthquakes and reactivate volcanic belts. The Yellowstone supervolcano might even erupt with a force 100 times stronger than usual. Oh, and the climate system would change dramatically. Air convection in the troposphere would speed up 3 times due to higher atmospheric density. The energy of extreme weather like typhoons and heavy rains would increase by more than 10 times. Typhoon winds could reach level 18, and daily rainfall might exceed 1,000 millimeters. The oceans would also be squeezed shallower. The whole planet would feel like it's trapped in a pressure cooker. The magnetic field would get stronger, making auroras brighter, but radiation would also become more intense. Satellite orbits would destabilize, and the moon's tidal force would be amplified, leading to one tsunami after another. In the end, this planet wouldn't turn into a black hole, but it would become a scorching, violent, hell planet filled with lightning and flames. Life might still exist, but it would no longer be our home. What would happen if the meteorite that caused the mass extinction hit the Mariana Trench? Alright, let's set up the Chicxulub impact on the Mariana Trench. Wow, at the moment of impact, it releases energy equivalent to 3 trillion Hiroshima atomic bombs. The impact zone looks worse than my grandma's homemade apple pie, completely dreadful. The 11-kilometer deep seawater offers no cushion, and the seawater within a 1,000-kilometer radius instantly turns into plasma, forming an 800-kilometer wide liquid scar. The initial height of the tsunami waves generated by the impact can reach 500 meters. They will hit the Japanese archipelago in 6 hours and destroy all Pacific coastal cities like Los Angeles and Sydney within 24 hours. Even after the aftershocks travel around the Earth, they still maintain a height of 5 to 10 meters. At the same time, 300 trillion tons of dust are thrown into the stratosphere. The amount of sunlight reaching the Earth's surface drops sharply to 0.03% of its normal level. Large-scale plant death leads to the collapse of the food chain. Oh, that's not good. The impact momentum also causes a 12.7-degree shift in Earth's axis, shortening the Earth's rotation period by 1.8 hours. All 327 active volcanoes around the Pacific Ocean are activated, and the supervolcanic ash columns further worsen climate deterioration. Well, only tardigrades in the Antarctic ice sheet and tube worms near deep-sea hydrothermal vents might survive through extreme adaptation. Complex life would take hundreds of millions of years to recover, far longer than the 10 million-year recovery period after the Chicxulub impact 66 million years ago. What if the meteor that caused the mass extinction hit the moon instead? Alright, let's just have the Chicxulub meteor hit the moon this time. Whoa, the energy released at the moment of impact would be equivalent to 1 million times the total energy of all nuclear weapons on Earth. It would instantly melt rock several kilometers thick, forming a complex impact crater over 200 kilometers in diameter, similar to the moon's Copernicus crater, and also similar to my grandma's homemade apple pie. At the same time, it would hurl trillions of tons of lunar rock into space at speeds exceeding the lunar escape velocity, creating a massive cloud of debris. Hey, that's actually kind of interesting. Surprisingly, this debris would have only a limited impact on Earth, with the survival rate of life remaining above 90%. Only about 5% to 10% of the fragments would be captured by Earth's gravity. Small fragments would form a global meteor shower, while fragments larger than 10 meters would only trigger local impacts with the equivalent force of a megaton-scale nuclear bomb. 10 trillion tons of dust would enter Earth's stratosphere, but it would only reflect 5% to 10% of solar radiation, causing a global average temperature drop of 1 to 2 degrees Celsius for a few years. This is far milder than the 6 to 10 degrees Celsius cooling that occurred when the meteor hit Earth, and it would not disrupt global photosynthesis. Well, the stability of the Earth-Moon system would also remain unshaken. The moon would stay in its orbit 384,000 kilometers from Earth, maintaining its tidal-locked state. Earth's ocean tides and climate regulation functions would remain largely unaffected. If this meteor had hit the moon during the age of the dinosaurs, large creatures like dinosaurs would not have gone extinct, and the rise of mammals would have been delayed. Life could have avoided a global ecological collapse by migrating or evolving to adapt. What would happen if we swapped the positions of the Earth and the Sun? Alright, let's go ahead and make the switch. Wow, at the very moment of the swap, Venus was immediately devoured by the Sun, and the entire solar system instantly fell into chaos. The Sun makes up 99.86% of the solar system's mass, while Earth's mass is only 1/300,000th of that. With such feeble gravity, Earth simply cannot hold the other planets in orbit. Mars, Jupiter, and the rest of the planets drift away like kites cut loose, vanishing into the depths of space. Interestingly, however, Earth clings tightly to the Sun, staying within the habitable zone. After such a cosmic shuffle, less than 10% of life on Earth is lost. Without the gravitational shield of Jupiter and Saturn to intercept asteroids and comets, the chances of Earth being struck by large celestial bodies skyrocket, more than 100-fold. Solar flares and prominences would bombard Earth's magnetic field directly, triggering global geomagnetic storms that destroy all electronic devices. The atmosphere would gradually erode under constant solar activity, while solar wind particles penetrate the ionosphere, increasing radiation levels at the surface. Maybe after a few hundred or thousand years, Earth would be crawling with nothing but Hulk-sized green giants.